So it's my question, Alexei Mailybaev here. We'll talk on renormalization group of inviscid.
Okay, so good afternoon again. So I said that part of the people were at the yesterday lecture, so I will try to make the motivational part short, and then we will just go directly to the modeling. So this is a joint work with Artem Raibekas from the University of Niterói in Brazil. So I recall. So what was the motivation? Motivation was to consider the models, which are toy models of turbulence. So the idea of turbulence. I'll first recall you. So what is the general idea that? What is the general view of turbulence is that you have you force something at large scale. For example, you take a pot of soup and mix it. So you do the forcing, and you force it at certain large scale. We call it L0, and there is a time scale tau 0. And then that large vortex, we say that the state of the vortex is determined by the variable U0. It can be, well, for example, think of an angle. And then this vortex creates smaller vortices, so through the interaction it gives you smaller vortices. We call it U1 at scale L1, time scale tau 1. So L1 is, think of the size, tau is a period, turnover time. And so on, and this extends to something very, very small, at scale L capital N, tau n. And the important part is that is a scale invariance. So the scales change as a geometric progression. So what we take is Ln is together, and so we consider the scale invariant version is when the time scale and space scale and time scale they scale in the same way. Let's say as negative power of 2. So size 1, 1/2, 1/4, and so on. And Un at each scale belongs to a certain space. So I will have a very simple space, but generally most of the results they extend to at least to complete separable metric spaces with group operation. So that's can be rather general space, and we will think of it as a model of turbulence. So as we discussed today during the lunch, so that there is some restriction of this view on turbulence, because in general, in turbulence, what happens is that the scale of time is certain power of the space scale. And actually, the fluid dynamic models they have this symmetry with all alpha together at the same time. So this is a let's say simplified vision of turbulence. So it will be already sufficiently complicated, and will have the phenomenon that we want to study, but it's still one step far from the full model. Probably what you can think of the model which looks like that, and this is a work of the student that we collaborated from Urbana-Champaign. So, for example, think of the pendulum, where the first leg of the pendulum is L0, and then you put some mass M0. Then second leg of the pendulum is L1, and you put mass M1. Then third pendulum is M2, leg L2, and the sizes and masses they decay in geometric progression. So you get a system which is finite length, finite mass, infinite dimensional, and then it's kind of whip, model of the whip, and then you force it at the large scale and see how it behaves. So the idea is to show that in some robust there is some robust situation where the solution of these kind of systems, despite they are formulated deterministically, but solution are probabilistic. So the dynamics of the system is represent a Markov process. So okay, so let's start with the model. So model that we consider discrete time. So the time will be taken as in time intervals corresponding to turnover time at each scale. And this means that our space-time, this is space which we label it 0, 1, and so on the scale, and then there is a time. So we have different scales, 0, 1, 2, 3, 4, and so on. So at the larger scales, the time step is 1, right? Because at the larger scale, which is size 1, time step is also 1. So we consider only integer times. At the first scale, which is 1/2, so the steps are twice smaller. Then at the next stage is 1/4. Then and so on. So that's let's say simplest space-time that you can arrange, which is compatible with scale invariance. So if you have scale invariance, so the space and time scales they change. So the space-time which is invariant under scaling. So if you multiply by 2 time and scale, it will be the same lattice. So this is monofractal lattice. So what we say is that we have n and t is a space-time, n gives you scale, t is time, and they point on lattice. So L is a collection, is a set which labels all the points, and then what we will consider solution, state of the system. The field is a collection of the values of the variable. So at each point we have a variable. So here, for example, will be u1 at the time 3/2, right? So at each point you have a variable. So the full field is well. So if u is in x, then full field will be in x power L. So it's a product space, and we will work with product topology. So everything is understood in this way. Okay. So then the next state is equations of motion. So equations, they should be scale invariant. So scale invariant equations mean that they are the same. So at each point, at all points, they are the same. So it means that scale invariance of the equations mean that the equation written and proper scales, they are the same everywhere. So it means that we can just put so how we put some model which is more general that we considered last time. just to give more freedom for different models. So what we do is we consider the same interaction in each cell. So what you can think of is that at each cell you take two values, and whenever you know these two values, they give one of them gives a value on the upper corner, another gives you a value on the lower corner, and then
is a rectangle?
Rectangle, yes. So that there are two functions, f and j. So there is function f from x squared to x, and there is function j to x squared to x. So whenever you have two values here, it gives you value right there. There is and another function gives you value here. If there are two values coming from different sides, because from here there will be, you can see from here there will be also two values coming, right? Oop. Then you just take sum of them. So that's a model.
What is that? Sum?
Take a sum. Take a sum. So I will not write equation of motions. Just I hope it's clear. So this is a problem, and now our goal is to solve a Cauchy problem. Cauchy problem, we solve it. So what it means? It means that we give initial condition. Initial condition that n at 0, let's say it's certain number an for on n from 1, 2, 3, so on. And then, so we give initial condition on the left, or here, at time 0. And also, since we have interactions from both sides, this is what we didn't have last time. We only had interaction from below. But now we have interaction. So large scale in smaller scales, and smaller scales influence larger scales. So we need to give boundary conditions here to make it consistent. So at 0 scale, we force. So here we give boundary conditions. So with the whip, it means that we give a forcing, and we give initial state. So the question, how we solve now this problem? So what is the solution? Okay. So before having the solution, I will give. So there will be
initial conditions are the column.
Initial condition is a horizontal side, and the boundary condition is the initial condition is vertical side on the left, and boundary is a horizontal up. Because if you want to know the value here, you need to know what is up there.
So B is 0 is A0.
B is 0 if U 0, 0. So you may think, for simplicity, you just can put them 0. So you can think that you put 0 here. But you need to put some extra condition on the top, because otherwise you cannot just, there is always arrow coming down, so you need to define something from above. Well, at least this is how we formulate, because this is, let's say, this is physically motive. This is essentially what means large-scale forcing in turbulence. So you force, or you take a spoon and start to rotate. So this is B, and A is the initial condition. It's what was at certain time 0. So the example that we will consider through the whole lecture is there will be 2 examples, and actually we can make it simple, even simpler than we had before. We will consider state which is 0, 1, symbolic. So it's every point we just put 0 or 1. So you think 0 is vortex is not active, 1 is active, or laminar turbulent. 0, 1. That's simplest way, and it means that we just need to give a function which give to two values 0, 1, give you 0, 1, and what. So there's actually it implied that there is 64 models of this type. So we will consider two examples. So example A. So essentially, what you need to know, given two values, what will be the next two. So empty circle will be 0. So it's 0, 0 should give 0, 0. This is always what we want. So if there is no motion cannot create any motion. And then 0, 1 gives us 0, 1. So nothing changes. Then 1, 0 gives you 0, 1, 1. And 1, 1 gives you 0, 1. Just an example. This is just an example of these two functions. Upper part is f, lower result is g. And example B will be, so it's 0, 0, always 0, 0. 0, 1 gives, this is also the same. And the others will be different. 1, 0 gives you 0, 1. So this interaction is different, and this interaction will also be different. And then you add in Z2. So 1 plus 1 is 0.
What are the interpretations of these functions of mg in terms of the weak? Do they have interpretations?
Well, in interpretation, yes. It's, for example, if there is these two vortices are not active, they remain not active. For example, if larger is active and this is not, it starts motion at smaller scale. And if they're both active, then this dies out and this remains. So it's kind of interpretation you can think in that sense. So in general, you have some interactions, and considering the simplest possible version of the space, there are just 64 possibilities, and we take 2 of them. As an example. In principle, of course, space X is generally more complicated.
Do we always assume the orientations of the vortices are the same?
No, there is no orientation at the moment. You see, it's just 0, 1. There is no orientation. It's just 0, 1. Analogy. Vortices, I just was talking about vortices to have some geometric view. In turbulence, it will be vortex. In a whip, it will be angle of each section, right? So that's, and we want in the whip it will be angle of each section, and here we will just make an abstract model which has this structure. So now there will be a few results which actually show that analogy that these kind of models are really capture many things that we know in partial differential equations, because this is on partial, or at least infinite dimensional system with this scaling. So first we can define what means weak solution and strong solution. So we can define what is weak solution. So first of all, strong solution. So U and T is a strong solution if it satisfies equations at every block. If it satisfies initial condition, it satisfies boundary conditions. And So if so strong solution must satisfy equations, initial conditions, boundary conditions, and it so in partial differential equation, when what means strong solution is that it belongs, for example, it's differentiable, right? So it belongs to some good space, which means that there is a fast decay of motion at small scales. So so here the fast decay of motion at small scales, here there is no, it's just 0, 1. So the only way how you say that it decays at small scale is that un is just 0 for sufficiently small, large n. So at sufficiently small scales, just have nothing. So if you have this definition, what you can prove is that for any that the local, you can prove local in time existence and uniqueness of solution. So you give me initial condition from that class. Locally in time, I can guarantee that there will be certain time interval when then this type of solution will exist, and it will be unique. And another thing, you can show that this solution may blow up in finite time. So that I want you to show. I want to show you in for the two examples. It stops to be strong solution. So essentially, this second condition is violated. So it means that the 1 should appear at an infinitely small scale, and you see it directly in this picture here. So this is a model A, and we put initial condition 1, 1, and then 0. And what happens is that after time 1/2, one carries there, 1/2 is there. So in time 1, you get the ones already. You have more active states at infinitely small scales. So essentially, it's something like you have in Burger's equation analogy. And the same happens in the model B, just in slightly different way. Because just dynamics is different, because interactions are different, we put initial condition, and also it propagates to infinite time. At finite time, it propagates to infinitely small scale. So that's what we have. So that means that so this situation is very much similar to what we have in ideal systems for partial differential equations for this kind of turbulence-like model. So then we can put the second definition. The weak solution.
When a PD blows up in finite time in a concrete situation, you see faster and faster things happening at finer and finer scales.
Yeah, that's exactly the situation that we see. So the weak solution is, let's call it A, call it B. So when we only have A, so only satisfy equation, initial condition, boundary condition. But we don't care about what happens at most scales. So in that case, we can just prove that global in time existence, but generally nonunique solution. So if you don't ask that the solution becomes 0 at small scales, you always have a solution. You can always satisfy initial condition, boundary condition, all equations. But the problem with that solution at all times. So it means that you can continue Z solutions after the blow up. But generally they are non-unique and you can prove it. So essentially you can prove for this system just directly by hand that the solution is unique until its time 1/2. And then there are infinitely many there are more than one, because it slips. So there is more than one continuation in a weak form, because there will be something there. Okay. So, yes.
Why is A sounds slightly better in your situation than a weak solution sounds to me in the PDE solution? Because I know the definition, but I don't see the fact that there's something.
I can say why it's weak. Yeah.
Language fits, but it's not.
You see, this is when I say that they satisfy all equations. Why it's in a weak sense? It's because actually they satisfy in a weak sense in the sense of the. So it's a point. Each equation is like you may think as a collection of all equations as a full system. So when you check just single equation, it means that you test it. It's kind of it's similar to the integration with a test function. I say that I test this equation. It's satisfied, yes. Then I test this function. Satisfied, yes. Is it?
Well, so maybe you could say, in the PD case, if you imagine rewriting your equation on the Fourier series.
Yeah, exactly. And then at every level you separately verify. That will be a weak solution, yes. Yeah.
You can do that?
Yeah,
interpret it at the Fourier scales?
Yeah, that's actually kind of one of the interpretation, yeah. That's.
He agrees, you agree. Okay, good.
So I think thank you. It's a delicate question. Okay, so we know that we cannot solve, and so that's good. So the next step is what we do is. So it means that in general, we cannot solve the system, and the right thing is to define a regularization. So if we not solve the system, what we do, like we now remember that in a realistic situation, this scale invariance does not extend to infinitely small scale. It stops someplace because there is a kind of dissipative mechanism. There is viscosity at very small scales. So let's make it also. So we choose certain scale n capital and just put 0 below by force. So whenever we put 0 below a certain level, what is there is uniquely defined. This you can follow because what happens at every node is given by previous nodes. In this node is given by previous nodes. So in that way, there is just finite number of cells. So you either come to that level, to that line, or to that line. So unique way how to define solution inside for all times. So the regularization is given by demanding that un of t is 0 at n bigger than n.
But if you had real numbers here instead of just 0 and 1, you could ask that these zeros just be going to 0 exponentially fast.
Exactly.
And that would be like smooth.
Yeah, that will be like smooth, exactly. Yeah,
you don't have it.
Well, I want to be.
You don't have that.
Yeah. In that example, I have it in the sense it's just 0. You cannot make it smooth. But certainly these examples will are possible, but I want to stick to the model which will be easiest possible. So in the sense that if I have this phenomenon here, then this complication is not that important. That's philosophy. Okay, so we make a regularization, and then we automatically say that there is a unique solution. It's also global in time, and we call it UNT, and I put N capital on a superscript because it depends on where we cut. So the question, what happens when N goes to infinity? So whether we can, cutting lower and lower and lower, we really get to some, we choose some solution in the limit. Because if there is a convergence, then we get a weak solution that is chosen by the regularization procedure. So this is what we understand. We call.
By what?
It's chosen by regularization.
By what?
Regularization.
What do you mean? Specific. That's a name. Tell me what you mean. But I know. But logically, I can't say box on the chalkboard. I have to say choose an N or something. What does it mean to choose it?
I mean that choosing means that there is a limit of regularized solution when N goes to infinity. If this limit exists, the limiting object will be a selected solution. So this is what we call selected solution.
But it's selected by what choice?
By that choice, by that regularization.
What does this choice mean? Say it in words. Choosing the ends?
I don't understand.
What does it mean, the choice?
Just zeroing out below some fixed n and taking that.
No, but now he's taking a sequence of ends going to infinity.
And you make it smaller.
The sequence of ends going to infinity?
Yeah.
I don't believe you when you say that.
No, there is no choice. I say that if there is a limit, so assume that there is a limit of this solution as n goes to infinity. And this will be solution of the system with n equal to infinity.
You have the word choice. What is the choice?
Choice is to select
Then you talk
zero.
about it depending on the choice.
Selecting zero.
Yeah, because if you can put 0 instead of 0, you can put 0, 1, 0, 1, 0, 1. It will be different choice.
Is it independent of the sequence capital N?
It should be independent of the sequence capital N.
You're assuming that.
Yeah.
That's what I'm asking.
This is okay.
The choice is not the sequence.
The choice is not sequence. Choice is regularization.
Zeros.
Yeah.
Okay.
Yeah. Good. Thank you. Okay. So now let's just first understand why this sequence at all can converge, and in which case. So now what we will do, we will define an evolution map.
Oh, this is the definition.
Okay, I will write
This
it.
is line is the definition. Regularization means that this choice converges and success.
So far, everything is definition so far.
Is that line a definition or a statement?
Yeah, definition.
Regularization defines the fact that you converge uniquely is not part of that definition.
So if,
You're asking a question about the definition.
yeah,
Didn't see that.
if this converges.
Oh, okay. Thank you.
Okay, so another definition is we introduce evolution map. So we introduce evolution map, we call it phi n of A. So what it is, so it maps A is an initial condition. Remember that I said A is our initial condition. So it maps A1, A2, and so on to the UN at time 1/2. So it which maps what we have here to what we get. I don't want to break it. To what we get there. Okay, so solution is unique. Given any initial condition, we know what happens at 1/2. This we can do. So now,
Independent of the boundary?
yeah, in that case it's independent of the boundary because no errors come from a boundary. So that's okay. And actually, because of self-similarity, this I'm not going to enter into the details. But as soon as you know these maps with different n, you can reconstruct map to any time because of self-similarity. But let's not get into this detail. So now I want to construct. Let's assume that you have this map for one n capital. I want to construct the map for n+1. So what we have? We have. I forgot. The level 0 is not important. So 1, 2, 3. So this is our map. There's not enough space. Time 1/2, 0. So our map is what maps here, this place, to this vector. So now let's construct a map which corresponds to the regularization at one level lower. So what you can do, you can consider the self-similarity of this system, because this system at the period 1/2 is exactly the same as the system at time 1/4 in this cell. They just have the same form. Only the smaller system will be regularized at scale less than 1. So what you can see that if from here to here, so in other words, the large system is the same as these smaller blocks by self-similarity. So that means that this vector to this vector is carried by map Phi(n). This vector to this vector carried by the map Cn. So what you can prove is that Cn+1 phi, yeah. Actually, it's psi, but for some reason I started to write phi. Yeah, phi n+1. So what it is? It's a first you have to shift. So I will write a formula, then we will describe what it is.
No, psi.
And now it becomes psi.
Russians know these letters.
So what is this in the formula? So sigma plus, when you apply it to the vector, which is a1, a2, and so on, it gives you a vector which is a2, a3. Just shift. Sigma plus is a positive shift, which gives you initial condition, and it cuts the first element. Then you can go twice forward, and then sigma plus, no, this was sigma plus, and then sigma minus, what it gives you, so when you put a2, a3, and so on, it adds 0 on the top.
What does it say? It's quite hard to see in the vectors.
In the vectors, it shifts up, and this shifts down. Yeah. Physically, shift means scaling. So multiply scale by 2 or divide by 2. So she scales up and down, and twice phi. So this is the first part. This is how to come from this data to that data. And then there is extra cell that we did not take into account, is what happens in this upper cell. and this is controlled by Xi. And Xi is, we can write the equation for the Xi. Xi of A1 and A2 and so on. It's a vector where the first component is F A0 A1 and J A0 A1 and 0 0 0 0. Importantly, that Xi is just certain map which depends on these two functions F and J, and this is something universal. Okay, so far it's a bit maybe not that simple, but now I will rewrite it in a form that I think you all much more familiar. Function in the space. So let's consider the vector A, which is A1, A2, A3, and so on, where all AI is just 0, 1. And we are in a product topology. So this is the right, so we can just consider A to be a point on a counter set. So what you do if it's, for example, 0, 1, 1, 0, and so on, you substitute 1 by 2, put point in front, and this is a point on a counter set. Right? So convenience of the counter set is that it also brings the metric. It's the same metric. So we by considering this point on a counter set, we just preserve all the topological properties. So what it means that whenever for any function of this type that we consider, including the evolution map, it's just map from counter set to counter set, and it's actually a continuous map on a counter set. So what it means that Cn is a continuum map on a counter set from counter set to counter set. And now I can write this relation. So the psi n plus 1 shift means shift down. First shift up means that you. For any n capital, it's a continuous function, because we added zeros here. So it maps some collection of numbers with zeros below. It's automatically continuity in topology.
Oh, okay.
Yeah. The function. So the function from the initial condition to the so now this first was psi minus or sigma minus. Sigma minus was shifting down. And shifting down is in a counter set is just divide by 3. Right, so it's just shift of the number divide by 3. And then we take Cn by Cn. And then we have to, this is function of a number on a counter set. And then we have to shift up, which means 3a. And we have to add one more function. So this is a relation between two sequential maps. So this is Feigenbaum type. And this is characterized system. Characteristic to a model. Because this Xi is what carries information of what is F and G.
This is kind of a product, right? This is not a...
This is not product. It's a composition. It is a composition. It's not a product. It's a composition.
First go 1/2 time and then another.
1.5 time, yeah.
Yeah, but phi is supposed to be a function on the counter set. Now you're composing it.
Yeah, counter set to counter set.
Yes. Oh,
It's a function of counter set to counter set, so you can compose them, right?
why is it going to the counter set?
Because every Fn is a counter set to counter set.
Well, you're just repeating your statement.
Yeah, and then if you do it,
Conditions of point of the counter set. It reads, it eats A.
so you take point on a counter set.
The argument is A.
A is in counter set.
No, but A is the initial condition.
Initial condition, it's in the counter set. Because A is just
Why are the initial conditions in the counter set?
by definition, because I mapped the sequence of 0, 1, 0, 1 to a point on the counter set.
But it's only if you have 0, 1, 0, 1, the energy case. Is it if you have some other space?
Of course, some other space it will be more complicated. I just want to.
It's a product. I mean, whatever you take, it'll be a countable product. Like a countable product is 2 points, it's a counter set.
Yes. Product of Z2s.
Product of Z2s, yeah. It's infinite product of Z2s.
Yeah, no, but if you took another, he's asking about
Yeah, if you take another, it will be still product, yeah.
the infinite product.
It will be infinite product. Just I want to make this relation transparent. So, and also what is convenient is now I can plot visualize Pn because it's function. If it's different space, it's difficult to visualize.
What do you mean it's a function?
It's a function for real line. You can draw it on a piece of paper. It's a map. It's a map on counter set, which I can draw.
I don't mind you saying it's a map for counter set, but he just psychologically switched to the idea of a function.
Yeah.
Why is that a function?
Yeah.
You can't go to the line. And watch a real value function.
You're right.
I know, but I mean, I don't like that because
He learned the functions and maps as a set, so that is the problem.
No, you missed the point. You put the counter set on the real line, now it's a real value function. On the counter set to the real line.
Yeah, I agree.
I want to watch it carefully if he uses some property of function.
Yeah, I agree.
They're not mapping to the counter set, so. Math objects have meaning.
So that's how it looks like for that example A. So when we know what is initial map, when you take Psi1 means that you just put zeros right here everywhere. So it's this map you can solve by hand. It's 0, almost 0. So this is in green is a map 1. So this is map from counter set to counter set, but I connect points by lines, so you see. So this is the green one is a Psi1. And then you apply just the same operator every time. And this is 2, then red is 3, and so on, and then it converges. So you can see visually that it converges, and actually you can prove it in that case. You can prove that there is a global attractor. So there is a fixed point. So so what you can prove is that there is a fixed point of this operator for the example A. Example means that I define psi. So the difference between models is just different psi. So what you can prove is that this operation, which you can just call it renormalization group operator, which is phi, I'm sorry. So this transformation, and this transformation has a globally attracting fixed point. This you can prove just by brute force in the case A. So it means in the case A, so now you can just write it as a statement. So if it happens that that this renormalization operator that is applied to phi 0 infinitely many times. So if this limit exists in C CK topology. So if there is a fixed point attractor on that solution, then for any initial condition, you have a pointwise convergence of the regularized solutions. Converges to a solution of the ideal problem. So if we have a convergence on the level of the renormalization group, that means that for every initial condition, the solutions, regularized solutions converge. And the limit is just a solution of the original problem. And this you can. That's a
strong solution.
That's a strong solution. That's a strong. No, this is a. If you think about analogy with PDE, think of Burger's equation. So we regularize it, put viscosity, take viscosity to infinity. There is infinitely many weak solutions, but we choose the one with the shocks. This will be this. And actually, the example A looks like the choice of something which looks like a shock. So this is a picture. So we take initial condition. Remember, it blows up at finite time, and no matter how you regularize, in the limit you get continuation, which is just the same. There are infinitely many solutions that I can. Let's not claim it. So in an inviscid limit, I will have this continuation, uniquely chosen by the regularization limit. So the connection which is made is that connection between solving this between inviscid limit of solutions and the fixed point attractor of RG operator. This is the connection.
So you're sort of adding terminology from the field, selecting the weak solution, but actually that's not part of the official statement. The official statement is you have the truncated regularized thing. If this hypothesis holds, then these regularized things converge to a unique strong solution, period. Now you're saying this is a construction that proves there's a unique strong solution, and you're interpreting it as being, if you interpret the non-uniqueness statement where you don't regularize, you are selecting out of this huge basket of weaker solutions one solution. It's like an interpretation of the mass statement.
It's an interpretation. It's one side.
It's not a strong solution by your definition.
No, yeah, it's just one of the solutions.
It is a weak solution.
It's a weak solution which you selected.
So you have the definition of strong solution and weak solution. Strong solution at the extra stipulation that it's zero after some n.
Well, you could imagine putting in the exponential decay thing.
Yeah.
It stays in that space. I mean, that's what he's imagining.
No, but
No, this imagine is
That's what I'm making. There's a distinction between the. Okay, I see. This selects one of the weak solutions.
Yeah.
one of the solutions.
Okay,
Which is-
so I see. I was wrong. Okay. So,
it's more like
but I could see it as selecting a strong solution if you actually made it more like a PDE and had exponential decay. That would be C infinity.
yeah, if that's true. But I think the analogy of partners is a good one because there you really have a rough weak solution, but it's unique and selected by this type of regularization.
So in some sense, the ideals. Okay. So also another side of this interpretation is that if this fixed point of a renormalization group is stable, so it means that it will be attractor for different initial maps. So it would imply that if you change this, if you don't regularize with zeros, but regularize with anything else, it will still go to the same, selection will be the same. So whatever you put as in the regularization, and I take a limit, I will always select just the same solution.
But you have to put a solution.
So you have to put something. You can put 0, 1, 0, 1, 0, 1, for example.
And what do you do next?
And then I put it down.
No, but then it won't be a solution. That won't be a solution.
If I put whatever you put here at level n, and then I take limit of n goes to infinity.
No, but what do you put below there?
Zeros. Whatever. If you put whatever, if you give any deterministic rule, what you want to put here below. Oh, okay, put zeros below, for example. You put 0, 1, 0, 1, and then 0, 0, 0, 0. Yeah, below doesn't matter. Yeah, below doesn't matter. So whatever you put here, in the inviscid limit, you always select something, the same thing. And this is, again, similar to Burke's equation, because we know if you change viscous mechanism by some other dissipative mechanism, like hyperviscosity and so on, though there is no proof of that, as I understand, right? But numerically we see that we select always the same solution.
Burgers are supposed to be this extra stability.
Yeah.
An extra from the fixed point.
Okay, so that's a moment when that's a situation when there is a limit. So now, and it means that there is a fixed point attractor of a renormalization group operator. So the interesting situation is if the attractor is not fixed point but a measure. So now the next step is we imagine that dynamics of a renormalization group operator is chaotic, and the limit is a measure. And this example B.
In what situation did you have convergence, do you say? In which situation did this hold?
This holds in example A.
Okay, thank you.
Yeah, so if you take these interactions, this holds. If you take these interactions, this doesn't hold. So if this doesn't hold, this means that we don't have a limit. So these sequences diverge.
So this is an if and only if statement?
No, not if and only if. Let's say, if this is done, maybe it's on if and only if. I think maybe. No. Let's say in the case B, this doesn't hold and this doesn't hold. Right? At least for some initial conditions. So what to do if Rn C0 phi0 diverges.
Here, in case A, the first thing holds. Yes. The theorem as you wrote it looks a bit tautological, that if this holds, then that holds. But the point is you prove that the first...
No, you see, it's not the same statement. This is just map on 1/2 time. And this is at all times.
Okay, but it's believable from that first statement, the second one. But the point is, for case A, you prove that...
For case A, I prove the first line.
That's sort of the non-trivial thing. For that model, an additional non-trivial thing. Another statement. There's a second theorem for case A that holds.
Yeah, for case A, this holds.
Yeah. And in case A, there is one global
attractor. So now, if we don't have this convergence, what you do? We make another definition of regularization. We will make a stochastic regularization. And stochastic regularization means that instead of putting zeros, we put random numbers. x1, x2, 3, and so on. We put IID random numbers. So characterization means that we take un of t and we define as IID random numbers.
I don't know what it means to put things on the line. Because you put, I mean, I thought you had some equations.
It's a force. It's another force.
The forcing.
Just like the one at the top. It's just some
So
specific.
that's the B of T.
Yeah.
And now we put it below.
Why are you allowed to call that B of T? B of T was like,
This is B. This was B, and this is what.
your things there is like.
This is B, and this is X.
That's supposed to be notations, not concepts. Come on. What does it mean when you put something there?
What it means, well,
Model.
for a model, it means that I'm putting noise at small scale. So at small scale, at the level n plus,
Go ahead and change the state of the system.
I'm changing state randomly.
Huh?
Randomly change the state.
Go ahead and change the state, and then it evolves.
And zeros below.
No, but this is for all time. How do you change the state for all time?
It's like by definition. Or you mean physically or mathematically?
I understand what you mean. You're modifying your model.
I'm
Tell me how you're modifying.
So-
I understand your model. Tell me how you're modifying.
Okay. So how I'm
Not symbols, and ideas.
ideas is the following. So I keep the model exactly the same as it was up to the scale n, n capital. At scale n plus 1, I say that my variable is just random number.
Changing the rules.
At scale n plus 1, I change the rule. It's a random number at every time, IID. And then I put zeros.
And then you let it evolve.
And then I evolve it. So now the solution will depend on what you flip a coin. What is here? Okay.
At a certain scale.
At certain scale, and
Randomly change
yeah.
at a certain scale. Then you let it go.
and then I let it go. I evolve it here. Evolution happens in between.
What?
Real evolution is in between the.
Oh, it does influence going up.
Yeah, it goes up. The influence will go up.
Can I just think of this as just a boundary condition?
Yeah, boundary condition. I put a small scale boundary condition randomly. Physically, it's molecular noise. At small scales, we have random kicks.
Small scale force.
Small scale force, yeah. I'm finishing almost. So,
You change it. Okay. You change the model. We put the clock back to 0. We change the model by some oracle at a certain scale. We're going to change things. Then we're going to let this new model run from 0, from time 0.
and I say that,
Magically, it will do that.
and this is our new definition of regularization. So we give up with the regularization that we had before, put in 0 and put noisy regularization. Physically, this makes sense because what we did before, we put noise because we know that viscosity kills the motion at small scales.
There's the analog of the viscosity.
Yeah, that was before it was analog viscosity. Now we say that, okay, viscosity kills all the motion, but something always remains. There is small oscillation remain, which is molecular noise. So let's put them back. So this is analog of putting molecular noise into the small scale. And we put 0 for n bigger than plus 1. Okay, so that's our new system. We still have evolution. So now it's not an operator because it's not a map, because it's given initial condition at time 1/2 you have a probability distribution. So it's a kernel. Random map. So it's a probability kernel. Random map, or it's probability kernel, and we use the same letter. So what you can show is that just the same operation, the same thing works. So psi phi n plus 1 is, I will write with sigmas. So it will be sigma minus psi n, sigma plus, and then it's. So what happens is that now it's everything is a random map, so it's kernel. This is a deterministic map. Composition carries over the kernels. You have well-defined composition, how we define a kernel, and then instead of plus for the kernel, it's convolution, because sum of random. So essentially, you get the same expression. So you can what I want to say is that you can define a renormalization group operator, but now it's acting, instead of acting on maps, and now acts on random maps.
Maps on what?
Random maps. So giving random map for regularized at scale n, you get a random map regularized at scale n plus 1. So the theorem.
You have this self-similarity because these are IIDs, that's why you have...
Yeah, because they are IID. Mm-hmm. Yeah, because it's IID, so these are independent. Mm-hmm. So the theorem that if again this is true, if we have this convergence, now the convergence is in kernels. So I'm not specifying in which sense. It's somewhat slightly. There is a definition of what is weak convergence for kernels. It's slightly more than just weak. So let's not go into details. So weakly. So if there is this convergence, so if the dynamics converges to certain kernel, then the solution the regularized solutions, which are probabilistic now, right? So these are random numbers. Right? So solution is a collection of random numbers. So then the solution converges weakly to the collection of random numbers. So converges pointwise. Sorry. Then the distribution of regularized solutions converges weakly to a stochastic Markov process supported. Let me write, I will explain. Supported on solutions of the ideal problem. So what can be proved, that if the renormalization group dynamics has an attractor, so attractor now is probabilistic, so it's a measure. Then taking the limit of n goes to infinity, then so for each n we have a solution with a certain probability distribution, right? So for certain choice of x, we have certain solutions. So there is a probability distribution of solutions for each n. So now sending n to infinity, this distribution converges, and what you have in the limit is a Markov process. So you get a Markov process where each realization solves this system, solves all equations with given initial condition, given boundary condition. So the selection, so
the important equations were linear. It's important equations were linear.
No, these are not linear. This is Z2. These are not linear equations.
Well, why do the Markov processes satisfy those equations? You're adding up a bunch of solutions. What is solutions? By linear, I meant the equations were solved.
Yeah. It's just there are steps. Yeah, there is. You're adding it here. Yeah.
Linearity.
Yeah, that's. No, that will be. It's not important for the theorem that you add. No, the linearity is not important. Important is that. So important is the following. So what is important? So important is that the final system that we want to solve is a system which is formally deterministic. So it's a lattice with deterministic initial conditions, deterministic boundary conditions, and deterministic equation each cell. There is nothing probabilistic here. So now what I'm telling is that if you regularize it with noise and send it to infinity, this process will select randomly weak solutions. So it will not be one selected. It will be many different randomly select weak solutions. And the distribution of this selected solution has the form of Markov process. So what happens here depends on what was initially. Then the next step is also conditioned what happened here and so on. So that's and this Markov process is directly can be explicitly written in terms of the limiting map of the limiting kernel. So that can be proved. And now we can just see how it works for the case B. So the only case where we can really prove it is the case which I explained it last time for the Arnold cat. But for the case B, we can just see it numerically that it works. So case B. So case B is, so it's what? So you take C0,
So the problem is measured supported on weak solutions of the other problem.
Yeah, it's supported on the weak solution of the problem and supported in a way that it's a Markov process.
Yeah. And it fits with the time.
Yeah.
As a Markov.
Mm-hmm. So how it looks like, so this is one of the realizations. So we take the model B, put initial conditions, it blows up at time 1/2. So until this point it's all deterministic. And then we regularize it very far away. And every time, depending on how it regularized, you will get every time you will get something different here. So continuation will be different. But if you do it many times, you can compute, you can see what is the probability to be 0 or 1 at every spot. And you see that you have some well-defined probability distribution. And you can also check numerically that as n goes to infinity, the probability converges exponentially to certain values.
Is it sensitive to how you randomize?
In that case, it is sensitive how to randomize. In Arnold cat map, it was not. In that case, it's my suspicion is that there is certain conservation laws included there, which kind of make it sensitive. All what we see that there is a limit. The limit does exist. Yeah, it's not probably global attractor. So certainly it's not global attractor. It's just attractor in some sense.
In the case A, is it clear that this also can't happen? I mean, because doesn't it have to do with the stability of that fixed point? If you randomize the data, you would get...
Yeah, if you randomize the data, you just get the same.
So in that case, you would expect that is stable.
The stable, yes. In case A, it will be fully stable. Whatever even if you randomize, if you regularize randomly.
But did you prove that, or?
Well, it's quite clear that it's a case.
But it doesn't have to be. I mean, you could have a system where you get just one limit for any fixed forcing, but then when you add noise, you get some sticking out.
Well, actually, this is certainly can happen because out of the 64 models, there are some models with multi-stability, so the different attractors. So essentially, if there are several attractors, depending on how you regularize, you get that solution or that solution. So there is essentially there is a whole zoo that we have in dynamical system which can happen there. But the message is that we can interpret all the results of the inviscid limit in terms of the dynamics of the renormalization group operator and its attractor. So essentially, all what we see in the inviscid limit corresponds to the attractor of renormalization group operator, starting from initial point, and initial point. Let me write it. It's a kind of final message, and this is important. So we started with the ideal system, which is formally deterministic, right? Formally. And we needed a regularization. Because without regularization, there is no concept of solution. So now, ideal system, to every ideal system, we associate renormalization group operator. This operator, as you see, it only depends on, it only knows ideal part of the system, the interactions. So regularization gives us initial condition. So the way how we regularize only affects the first map. So the inviscid limit,
what does that mean? Inviscid limit, what does that mean?
I will write. N goes to infinity. It was regularization at scale. Yeah. It's related to attractors starting from that point. So inviscid limit is the limit of the renormalization group operator starting from the point which is defined by regularization. So that kind of mapping of the inviscid limit business to the single dynamical system, but for that operator. So this is duality that we want to give. So the duality is that whenever you have multi-scale, scale-invariant ideal system, it defines the renormalization group operator. Whenever you put regularization, it defines initial condition. And if you want to study inviscid limit, all solutions, all at once, for all initial conditions, they are associated to the limiting point of that renormalization group operator from that initial point. And there is a different situation. There is a situation when the limit is fixed point. It's analog of Burger's. And in the limit we have shock waves, solution Burger's shock wave. And what we expect in turbulence is that in turbulence the limit will be, the attractor will be chaotic. and then we expect that the limiting solution is a Markov process. And in other words, if you have a pot with a soup, and you take a spoon and turn it, actually solution is a Markov process. You cannot predict it. Because of molecular noise, already the way the potato will go after frittering over time is left or right. It's random. It's a measure. Triggered by molecular noise.
What?
Triggered by molecular noise.
Triggered by?
Molecular noise. Yes. So that's a true Markov process. That's at least, that's a conjecture. Conjecture for fluids. And so the whole motivation of this kind of study. So it's, at least I think that we succeeded to go to sufficiently simple systems where this seems to be tractable, and which still has that property that we want to see.
Well, if in a fluid you have some regions are turbulent and some not,
yeah.
How does this fit into that?
Well, this is perfectly well fit because this is because you see this you get in the limit you get certain probability kernel. You get probability kernel that gives you dynamics, but it may be deterministic. It may have deterministic form for some initial condition. It can be stochastic for another initial condition. For example, in the case B, it's deterministic until a certain time and then becomes stochastic. Until blow up time, it's deterministic, then becomes stochastic. And this is all encrypted inside of this kernel. So it can be, part of it can be Dirac, other part can be probabilistic.
And the part, these are the choice of initial conditions.
Yeah. Because this is a beast which contains information for all initial conditions. For some initial condition, it can give deterministic solution, or the solution which has some deterministic components. In other parts can be random.
Okay, let's digress.
Okay.